Dear students, in this video, we will see how we can use a decision tree in real life. Means decision tree's main application is it makes the searching process easy. How? Now, we know that decision tree is containing root node, internal nodes, and leaf node. But what the internal nodes are representing? It is representing the action. And the branches that are coming out of the internal nodes are representing the outcome of that action. And the final outcome is represented by leaves. Okay. Now, when we are representing decision tree for real algorithm, then searching can be from root node to the internal nodes to the leaf node. Now, the action of the child node is based on the action that is available in the previous nodes. Okay, so the action of the child node is based on action that was carried out in the parent node, and leaves are representing the final outcome of that action. So we are having two types of the searching, sequential search and binary search. Now, how we can use decision tree to find out a target element using sequential search and binary search, that we are going to see with example. Now remember that X is the target that I want to search in the decision tree. Now when I'm searching X at particular level of the decision tree and I'm comparing it with the ith item, then L is representing the level in my tree and I is representing the value that is existing at that level, means with which node it is being compared, that is indicated by I. Now, here we can have the tree that is shown in the figure. Now, how I can apply sequential search? I will start from the root node. Now, when I move to the left part of the root node, and if match is found, then simply the equal condition will be satisfied and I have reached the leaf node. So I will stop at this point. But if match is not found, then I should move to the right subtree. Then in that case, my search will move to the second node. Means the comparison will be carried out to the second node. Hence, I'm indicating it as a L of 2. Okay. Then again here, if the match is found, okay, I will stop there. Otherwise, the process will be repeated. So like this, I will come to a particular point, and if the match is not found and I have reached the final leaf node, then I can conclude that the target item is not existing in my list. So like this, we are carrying the sequential search. Now, what is the advantage of binary search over the sequential search is decision tree will be the most appropriate solution for the binary search, because in decision tree, we are having mostly two child nodes for your root node. And generally, we can place the decision tree as less values in the left subtree and greater values in the right subtree. Then, how we can apply the binary searching in decision tree is first, it will compare with the root node. If the match is found, the algorithm terminates. But if the target value X is less than the root node, then the search should be repeated in the left subtree. Otherwise, the search should be repeated in the right subtree. Means as compared to your sequential search, when I'm using binary search in decision tree, the time complexity is reduced by half. And here again, at the next levels also, if it is matched with the particular internal node, I will terminate. Otherwise, if it is less, again, I should repeat my process in the left subtree and right subtree. Now, let us consider the example where we are representing Huffman code using decision tree. Now, I know that these are the four codes represented by my decision tree, but I want to search 010. Then I will start from the root node. Then I will follow the path that is taking me to the 0, means left one. Then I will come to the next value as a 1, means right one. But here I have reached the leaf node. So I can't search the last value, that is the 0. So here I can declare that the particular code is not at all existing in my tree. Now when I want to search 011, then let us see whether it is available. 0 1, again it is coming to the leaf node and it is stopping. Now 0 0 1, how I can proceed? 0, then again 0, and then the 1. Now here I have reached to the leaf node, but all the bits are matched, so the target item is existing in my decision tree. So like this, search process can be carried out in decision tree. Now, what is the complexity of a decision tree? Now, how many rows are there in my data set? That is what the number of the training examples, that is represented by n. Then how many columns are there in my data set? That is the number of the features, that is represented by m. Then you have to take the multiplication of n, log of n and m, that gives me training complexity. And the big O of m will give me testing complexity. And the space complexity is whole and sole depending upon size of your decision tree, that is the depth of your decision tree. Okay, so these are the three formulas to find out the complexity of a decision tree. Thank you.